deep in the annals of Earth's history, roughly 359 to 299 million years ago, lies a chapter so bizarre and transformative that it reshapes our understanding of life on this planet. This was the Carboniferous Period, an era when vast, swampy forests blanketed the equator, pumping unprecedented levels of oxygen into the atmosphere. These conditions birthed a world dominated not by dinosaurs or mammals, but by colossal arthropods, insects, spiders, scorpions, and millipedes that grew to sizes unimaginable today. Wingspans rivaling eagles, bodies as long as alligators, and predators that could snatch prey midair with lethal precision. This wasn't science fiction. It was Earth's reality, driven by an atmospheric anomaly that would never repeat itself. To grasp the Carboniferous, picture a supercontinent in formation. The land masses that would become Pangaea were colliding, creating humid, tropical lowlands perfect for explosive plant growth. Towering club mosses like lepidodendron reached heights of 100 feet, their scale-like bark shedding like modern pine cones. Ferns formed dense understories, while primitive seed plants began to emerge. These forests weren't like today's Amazon or redwood groves. They were darker, damper, and teeming with decay. Fallen vegetation accumulated in waterlogged soils, forming vast peat bogs that prevented full decomposition. Over eons, this organic matter compressed into the coal seams that fuel much of our modern energy needs, hence the name Carboniferous, meaning coal-bearing. The magic ingredient? Oxygen. Photosynthesis in these megaflora released oxygen at rates far exceeding consumption. Estimates from geological models, fossil stomata density, and ancient air bubbles trapped in amber suggest atmospheric oxygen soared to 30 to 35%, compared to our current 21%. This hyperoxia wasn't just a background detail, it was the engine of evolution. In such air, fires ignited easily. Even wet wood could combust spontaneously from lightning strikes. Charcoal deposits in Carboniferous rocks attest to frequent, intense blazes that sculpted ecosystems. For life, though, it was a boon, especially for arthropods, whose unique breathing system thrived in this oxygen bounty. Arthropods breathe through tracheae, networks of tubes that diffuse oxygen passively from spiracles on their exoskeletons directly to cells. No lungs, no active pumping. This works efficiently for small bodies but falters at scale as diffusion slows over distance. In today's air, it caps insect size. The Goliath beetle or Hercules moth pushes the limit at a few inches. But with 35% oxygen, diffusion penetrated deeper, lifting that cap. Gigantism exploded. Experiments today confirm this. Rearing dragonflies in hyperoxic chambers yields larger adults, echoing ancient genomes still latent in modern insects. Enter the stars of this alien biosphere, the meganeurids, prehistoric dragonfly relatives like Meganeura monyi. With wingspans up to 28 inches, wider than a hawk's, these aerial hunters dominated the skies. Their 4 independently moving wings allowed hovering, sharp turns and dives at speeds modern dragonflies envy. Compound eyes wrapping nearly 360 degrees spotted prey from afar, while barbed legs formed mid-air baskets to crush victims. Fossils from France's Commentry site, discovered in 1880, reveal intricate wing venation like engineered lattices, strong yet lightweight. Meganeura likely started as aquatic nymphs, ambush predators in ponds, molting into airborne terrors. They preyed on smaller insects, amphibians, even proto-reptiles, with success rates over 90%. Not far behind were the Paleodictyopterans, ancient net-winged insects with spans of 15 to 22 inches. Unlike Meganeura's ferocity, these were gentle herbivores, sipping sap via primitive proboscises, the precursors to butterfly tongues. Their wings, veined like stained glass, included curious prothoracic lobes, possibly evolutionary remnants of gill-like ancestors. Fossils from Kansas's Elmo site show them as early flyers, predating true dragonflies by millions of years. They glided through canopies, exploiting the third dimension long before vertebrates mastered flight. On the ground, horrors lurked. Pulmonoscorpius kirktonensis, a scorpion from Scotland's Kirkton Quarry, stretched 28 inches. Cat-sized, armored in chitin plates like Black Knight's mail. Its pedipalps, massive pincers with serrated edges, crushed exoskeletons. The arched tail delivered venom potent enough for amphibians. Sensory hairs detected vibrations. Eyes scanned for motion. Perfect for ambushes in fern litter. It ruled forest floors, preying on arthropods and early tetrapods, unchallenged until oxygen waned. Even larger was Arthropleura, the millipede-like behemoth up to 8.5 feet long and 110 pounds, wider than a human torso. Trackways in Nova Scotia's Joggins Formation show sinuous paths through mud, implying a herbivorous lifestyle grinding vegetation with blunt jaws. Its segmented exoskeleton, interlocking like roof tiles, provided defense. Dozens of leg pairs propelled it through swamps. Widespread fossils from Europe to North America paint it as a common decomposer, turning forest detritus into soil. Then there's Megarachna cervini, once mistaken for a giant spider. Re-examination in 2005 revealed it as a eurypterid, a sea scorpion adapted to fresh water. At 21 inches, it swept riverbeds with paddle limbs, raking silt for worms and larvae. Its carapace mimicked spiders, but no webs or fangs. It was a bottom feeder in oxygen-rich shallows, bridging marine to terrestrial life. Trigonotarbids, spider-like arachnids from 419 million years ago, were smaller, up to 2 inches, but pioneering land predators. Armored, webless, they crushed prey with chelicerae. Fossils from Scotland's Rhynie chert preserve book lungs and sensory hairs, showing full terrestrial adaptation predating the Carboniferous peak. Even tinier but armored like tanks, Hallucigenia sparsa. Wait, correction. The script mentions leopard, but it's likely Hallucigenia or Lobopodians. Actually, it's Macaridia, the Excalibur worm. From Devonian reefs, these few-millimeter annelids wore calcite plates like chainmail, curling into impenetrable balls. Invulnerable but slow, they filtered detritus, vanishing as predators evolved. This arthropod empire thrived because vertebrates lagged. Early amphibians like Ariops grew to 6 feet, but needed moist skin and aquatic eggs. Reptiles, emerging with scaly hides and amniotic eggs, were small but poised for takeover. Hylonomus, a 12-inch lizard-like pioneer, laid the shelled eggs on dry land. A game changer. The Carboniferous wasn't static. Mid-period, rainforests collapsed around 305 million years ago. Tectonics raised mountains, drying climates. Peat bogs shrank. Oxygen plummeted to 25%, then 15% in the Permian. Giants couldn't sustain their bulk. Smaller, efficient forms survived. Reptiles, unhindered by water, diversified. Why no return to hyperoxia? Lignin. Evolved 400 million years ago for plant rigidity, it resisted decay, burying carbon and spiking oxygen. Then, White rot fungi evolved enzymes to break it down by late Carboniferous, recycling carbon as CO2. Amber preserves these fungi. Today, they and termites, evolving 150 million years ago, prevent massive sequestration. Fires in dense air-capped oxygen at 35%, creating feedback. Zoom out. Earth's oxygen history is epic. Great oxidation event, 2.4 billion years ago. Cyanobacteria photosynthesized, rusting oceans, killing anaerobes, rising to 1 to 2%. Neoproterozoic, 800 million years ago. To 15%, sparking animals. Paleozoic rise to 20%, then Carboniferous peak. Post-peak, drops and rises, Cretaceous at 25 to 30%, now 21%. Each surge drove complexity. Eukaryotes, Cambrian explosion, land giants. Modern experiments. Arizona State's 2010 fruit fly study showed size scales with oxygen. Dragonflies grow larger wings in 35% O2. Atmospheric density, 20 to 25% thicker, eased flight for Meganeura. Ecosystem ripples. Plants grew faster. Lepidodendron matured in 15 years versus redwoods centuries, less defended against herbivores. Spore reproduction gave way to seeds in drying climes. Amphibians ballooned, 15-foot temnospondals, but declined. Reptiles rose. Coal, Carboniferous legacy, sequestered forests now burned, slightly dropping O2, 0.001% per year. Ironic reversal. Exoplanets. Oxygen biosignatures signal life informed by Earth's shifts. Human biology. Our lungs. Hemoglobin optimized for 21% O2. Altitude sickness at low O2. Toxicity at high. Space. Mars terraforming needs Earth-like mix. Climate lessons. Rapid CO2 rise. 280 to 420 parts per million. Echoes past shifts but faster, driving adaptations, so extinctions. Life resilient. Post-Carboniferous insects diversified to 1 million plus species. Ongoing science. Amber gas analysis, stomatal counts, CT scans of tracheae. Models confirm gigantism limits. Behavior evolution. High O2-enabled active predation. Declines spur deficiency. Interconnected systems. Biosphere shapes atmosphere. Photosynthesis versus decomposition. Geosphere. Tectonics. Hydrosphere. Swamps. Modern echoes. Dragonflies retain ancient flight. Millipedes, armor. Carboniferous reinvented Earth. Giants gone, but lessons endure in a dynamic planet.